This is the second video on how to calculate empirical formulas. The first video used percent composition, or knowing the number of grams of each element in the compound. In this video, we're going to utilize how the chemical reacts to figure out the empirical formula. Now remember, the empirical formula is the lowest whole number ratio of elements in a compound. The mnemonic used is the poem: percent to grams, grams to moles, divide by small, multiply till whole. And in the first video, we either started at percent to grams or grams to moles. In this video, we're going to start with divide by small, based upon the law of conservation of mass. For a quick review, the law of conservation of mass states matter can neither be created nor destroyed in a chemical reaction, which can actually be restated to atoms can neither be created nor destroyed in a chemical reaction. And that's what we're going to use in this video. So I think the best thing to do is to jump right in and utilize an example to show how we're going to do this. You have a compound which is made up of carbon and hydrogen only. That's sometimes called a hydrocarbon. It's allowed to completely react, in this case burn or combust, with oxygen, and it will form 29.94 grams of carbon dioxide and 16.35 grams of water. From this information, we can calculate the empirical formula. What do we know? We know we have a hydrocarbon made of carbon and hydrogen, but we don't know the subscripts X and Y. We know that it is going to react with molecular oxygen, and it's going to form carbon dioxide and water. Now it turns out there are two ways to solve this problem. The first is called the mole method. The second is the percent composition method. I'm going to cover the mole method in this video. If you want to know the percent composition method, see me outside of class and I'll be happy to go over it with you. Now the mole method depends upon understanding the following. Carbon dioxide is made up of one carbon and two oxygens. So for every one molecule of carbon dioxide, we have one atom of carbon. So we can say the ratio of atoms of carbon to molecules of CO2 is 1 to 1. Additionally, for water, which is H2O, for every one molecule of water, we have two atoms of hydrogen. So the ratio of atoms of hydrogen to molecules of water is 2 to 1. And that will become important down the road. So all of the carbon and the carbon dioxide has to come from the hydrocarbon because it's the only source of carbon. That's what the law of conservation of mass says. So the mass of the carbon in the hydrocarbon has to equal the mass of the carbon in the carbon dioxide. Same number of atoms, same mass. Since the masses are the same, then the number of moles of carbon in both the hydrocarbon and the carbon dioxide have to be the same. We know that the ratio of atoms in carbon dioxide to the number of molecules of carbon dioxide is 1 to 1. So the moles of carbon in CO2 has to equal the moles of carbon in CO2. So now we can calculate. Grams divided by molecular weight equals moles of carbon, which is 0.6803. But since it's a 1 to 1 ratio, it's also the number of moles of carbon that are in the hydrocarbon. So we can write that up here. We can do the same thing for the water. All of the hydrogen in the water came from the hydrocarbon. So the mass of the hydrogen in the hydrocarbon has to equal the mass of the hydrogen in the water. Same mass, same moles. But we know that the number of moles of hydrogen in water is equal to twice the number of moles of water because there are two atoms of hydrogen for every one molecule of water. So we calculate the number of moles of water. Because we have that information, we double that up and now we have the number of moles of hydrogen in the hydrocarbon. We can put that here and we see that we can now divide by small. So we're going to divide both of these by 0.6803 and that gives us 1 and 2.667. And the 6 in the 10th place is obviously not a 0 or 9. So now we need to multiply till whole And when you do that, you see that 3 will work, and you'll end up with these values, which can be rounded to 3 and 8. So we can say the empirical formula is C3H8. Let's go on to a second example. Toluene is another hydrocarbon. It's allowed to react with an excess of oxygen in a combustion reaction, and so carbon dioxide and water will be produced. You are given the values of the carbon dioxide and the water. What is the empirical formula of toluene? Stop, figure it out, come back, check your answer, and we'll go through it. Go. And the answer is C7H8. How did we get that? Well, we start by writing out the skeleton reaction, and we run through the same logic. All of the carbon in the CO2 had to come from the toluene. So the mass of the carbon in the toluene equals the mass of the carbon in the carbon dioxide. Therefore, the moles are the same in both of those. We know that because of the 1-to-1 ratio of carbon to carbon dioxide, that the moles of carbon in the CO2 equals the moles of carbon dioxide. We calculate out the moles of carbon dioxide and get 0.1332, and that has to equal the moles of carbon. So that gets put up here. Now we're going to do the same thing for the hydrogen, because all the hydrogen in the water has to come from the hydrocarbon. So the masses have to be equal. The moles have to be equal. We know that because of the 2-to-1 ratio of atoms to molecules, that the moles of hydrogen in the water is twice the number of moles of water. So we calculate out the number of moles of water, we double that, and we get this value for the moles of hydrogen. Now we can divide by small. So we divide each of them by 0.1332, and once again we get a number that cannot be rounded, because in the 10th place for the hydrogen, it's not a 0 or a 9. So now we need to multiply till whole. You start by multiplying by 2. If that doesn't work, go to 3. If that doesn't work, go to 4. So on and so forth until you get a number that does work. In this case, that number happens to be 7, because when you do that, you get 7.9. That can be rounded. When you round them, you get C7H8. So the empirical formula is C7H8. A third, and quite honestly slightly more complicated problem is this one. Methanol, otherwise known as wood alcohol, is composed of carbon, hydrogen, and oxygen. This is called a carbohydrate because it has carbon, hydrogen, and oxygen. You've got a 0.320 gram sample of methanol, which is allowed to react with an excess of oxygen, and it forms carbon dioxide and water. What's the empirical formula? I'm going to walk you through this rather than just have you do it on your own. You start by once again writing out the skeleton equation. Notice that it's now CXHYOZ. Based on the law of conservation of mass, all the carbon in the carbon dioxide had to come from the carbohydrate. So we go through the same steps. We know that the mass of the carbon has to equal the mass of the carbon. So the moles have to be equal. That is a 1-to-1 ratio of carbon to carbon dioxide. So we calculate out the number of moles of carbon dioxide, and that's the moles of carbon. We can do hydrogen in the same way. The masses have to be equal, so the moles have to be equal, but the moles of hydrogen is twice the number of moles of water. So calculate the number of moles of water, double it, and now we have the number of moles of hydrogen in the carbohydrate. Okay, the oxygen. All the oxygen in the product does not come just from the carbohydrate. Some comes from the molecular oxygen. So we can't quite do what we did for the carbon and hydrogen. However, we know the whole is the sum of the parts, and we were given the total mass of the sample. So the mass of the carbon in the methanol plus the mass of the hydrogen in the methanol plus the mass of the oxygen in the methanol equals 0.320 grams. This can be rearranged to say 0.320 grams minus the mass of carbon minus the mass of hydrogen equals the mass of oxygen. And we do it this way because since we know the number of moles of carbon and hydrogen, we can calculate the masses. So the mass of the carbon is moles times molecular weight equals grams. And we can plug that value in. Do the same thing for the hydrogen. Moles times molecular weight equals grams. Plug that value in. So the mass of the oxygen in the carbohydrate must be 0.160 grams. 0.160 grams divided by 16 grams per mole. The molecular weight of singlet oxygen is 0.0100 moles. So now we have something that looks like this. We can go divide by small, which is the 0.010. We're going to multiply till whole, but we don't really need to do this because they're all nice whole numbers. And so the empirical formula here is CH4O. So to review, You can calculate an empirical formula from information from a chemical reaction. This will usually be given as a combustion reaction, the ones that we did, but it does not have to be a combustion reaction. This all depends upon the law of conservation of mass. Matter can neither be created nor destroyed in a chemical reaction. If it is a combustion reaction, the moles of carbon equals the moles of CO2 because the ratio of atoms of carbon to molecules of CO2 is 1:1. The moles of hydrogen is equal to twice the number of moles of water because the ratio of hydrogen atoms to water molecules is 2:1. And if you're dealing with a carbohydrate or something that's not just two elements, you may need to work backwards to get the mass and then convert to moles. And that takes care of how to calculate empirical formulas. In the next video, we're going to go up the next step to actually figure out what the molecular formula is for a compound.